we continue with the least action principle for the scalar fields. So we have obtained from some simple considerations the following two-dimensional action. dA phi, dA phi. We fix k bar to be 2, k bar to be 2, and also c bar we fix to be 1. So as if we are in two-dimensional space-time. We want to obtain equations of motions that follow from this simple two-dimensional action. So how do we do that? So we have two-dimensional space-time. Let me draw it. By the way, we assume that t is also ranging from -infinity to +infinity, unlike it was written in the previous formulas, because for the fields we usually consider complete space-time. Well, actually, by the way, let us restrict. No, we can actually consider variations within finite regions. That will be important. Probably it's better. Okay, anyway, so there is some domain of two-dimensional space-time where this is defined, this domain D. This is a domain D. So it's some finite range of time and finite range of x. And there are some boundary conditions specified for the phi. Well, we will assume that phi is fixed at the boundary. Phi is fixed at the boundary. So we vary phi. So for every point of space-time, we have a value of phi, x0, x1, value of phi, and we vary it such that it is fixed here. So the variation of phi is 0 at the boundary of the region D. What does it mean that we vary? We have some value of phi here, and then at every point, and then we deviate it a little bit, delta phi, shift either to this side or to this side, and see how the action is changing. So the variation of the action is just the difference of phi plus delta phi minus s of phi and to linear order in delta phi. So minimal least action principle says that the equations of motion for phi follow from the minimal value of this action. At its minimum, or at its extremum, the variation is equal to 0. So we want to finally, after finding the variation, we want to finally put it to be 0. So let us see what this guy is. Delta S is then just d2x, dA phi plus delta phi, dA phi plus delta phi, minus integral over d2x, dA phi, dA phi. We just written this difference, and we remember that we want to find this difference to linear order in delta phi. So we expand. Well, what does this mean? This is just d2x, dA phi, d plus dA delta phi, dA phi plus dA delta phi, minus dA phi, dA phi. Now expanding these brackets, and because we want to keep only terms linear in delta phi, so the 0 term in delta phi expansion cancels with this one. So what remains is just d2x, dA phi, dA delta phi, plus dA phi, dA delta phi. But these two guys are equal to each other, so it means that this is just equal to d2x, dA phi, dA delta phi. Now we want to get rid of the differential acting on delta phi because we want to put this to be 0 for any delta phi. But how do we do that? We have to do the partial integration. Let me clarify how that should be done. First of all, let me write the following expression, that dA acting on, let me act like this, dA phi is equal to, times delta phi. This is total derivative. And this is equal to dA phi, according to the Leibniz rule. This is equal to dA delta phi plus dA phi times delta phi. So according to the Leibniz rule, we have that this differential is equal to this one. And now integrating both sides of this equation, we obtain that this expression is equal to 2 integral of the total differential dA over dA phi times delta phi minus 2 integral over d2x dA phi acting on delta phi. What remains to be shown that this is 0. That's we're going to show in a moment, explaining some mathematical ideas. But once this is 0, remember that minimal action principle demands for this to be 0 for any delta phi. And if this is 0, then the equation of motion that we obtain is this one, which is famously known wave equation, because what is written here is just d2 over dx0 squared minus d2 over dx1 squared acting on phi is equal to 0. Remember that dx0 is just time. So this is just famously known wave equation according to the rules. So now let me show that this is 0. How to show that? Well, this region D has arbitrary shape. It's not necessarily rectangular. But let us consider this integral for the rectangular case. That, for example, dt is ranging from t1 to t2, and dx is ranging from x1 to x2. And what we have here is just dA of some VA. VA is this guy. And what is this? This is nothing but integral over dt from t1 to t2, dx from x1 to x2, d0, v0, which is differential with respect to t, plus d1 to acting on v1. So now consider this term first. What do we obtain? We obtain the following situation. We obtain the integral over dx from x1 to x2. And this is integral over dt over the total derivative. What is that? This is just v0 at t1 and t2. Plus, similarly for this term, we have integral over now dt from t1 to t2, and integral over dx over the total derivative, which is just v1, x1, x2. So what do we obtain? We obtain geometrically, this is the following situation. We have a rectangle from t1 to t2 and x1 to x2. So we have integral over this side of v0, over this side of v0, minus this side over v0. This is the first thing. And similarly, this guy is integral over v1, so it's something directed along x direction, minus integral over this side over v1. So what all this means? This is just integral over the boundary of this rectangular shaped region over the d sigma a times VA. And what is sigma A? Sigma A is just normal vector to the boundary of this region D. Normal vector. Because you see, we integrating over the boundary the vector which is normal to this boundary. So this is we have shown for the rectangular region. If we have arbitrarily shaped region, we can slice it by rectangles. And for every rectangle, we will obtain this formula. These terms cancel out between each other. What remains is the integral over the boundary of this arbitrarily shaped region. So this, for arbitrarily shaped D, is nothing but the integral over its boundary of d sigma A VA. So this guy here is just integral over the boundary of this guy. But delta phi on the boundary is 0. As a result, this term is 0. So I explained to you how to perform minimal action, to use minimal action principle to derive equation of motion in simple settings. I explained to you simple means how to obtain field theory as an infinite number of ordinary mechanics. And I also explained to you basically Stokes theorem or Ostrogradsky Gauss theorem. I don't remember proper name for this theorem. But this is very simple mathematics.